Today we're joined by Dr. Sara Vasconcelos, Senior Scientist at the Toronto General Hospital Research Institute and Associate Professor in the Institute of Biomedical Engineering at the University of Toronto. Her research focuses on tissue regeneration in cardiovascular diseases and diabetes by finding ways to create new blood vessels to support cell transplantation. Hi Sara, welcome to the show.
Thank you so much for having me.
So heart disease is a leading cause of death and disability in Canada. How is your research helping to understand and better manage heart disease?
In my lab, we're really looking into how we can better support therapies for heart disease. So when people usually have a heart attack, or even people that have diabetes, which have a higher chances of developing heart disease, those can affect the heart and can lead to a heart attack. And then often the options are limited. So if you really go into heart failure, you need a transplant. And we all know that there aren't enough hearts from donors to meet the demand. So the idea here is to be able to better understand these diseases and what happens when you transplant the cells into these people with cardiovascular disease or models of cardiovascular diseases and diabetes, and understand how our therapy works to better improve it. So stem cells are a great one. We know that we can differentiate the heart cells that beat, so the contractile cells of the heart, which are the cardiomyocyte, from stem cells. And it's amazing because you can get so many of them, and it would be amazing to be able to put them back into that scar tissue that forms in the heart, to be able to remuscularize it, right? But what we have learned, and this is not just our lab, but many in the field, is that every time you try to transplant these cells, between 50 to 90% of these cells die. So it's really hard to, fulfill that promise of the stem cells without having them survive. And one of the main issues for their poor survival is because they don't have blood vessels. So we know that the blood vessels in the body deliver oxygen and nutrients to all the cells, and the same happens in these diseases, right? So what my lab we're doing is we're basically right now using vessels from fat and transplanting them into the heart. So you can think about this as recycling. You take an organ that you don't really need to survive, which is fat, and you chop it up and you process it, and you take those little pieces of vessels that you can combine with the stem cells, the cardiomyocytes or other cell types, and put back, in this case, in the heart. And we've shown that these vessels really bring in blood really fast and help the cardiomyocytes survive. So now, with the help of the stem cell network, we're really looking into advancing these studies into better models that are more close to human, so you can really understand whether this is going to be worth it to test in the clinical setting.
So your work involves a lot of cutting-edge technologies like organ on a chip. For those that may not be familiar with that, can you explain what it is and how it could potentially revolutionize how we both study and treat heart disease?
Organs and chip are a creation that we do in the lab where we engineer different organs in vitro. And they are not real organs, but they allow us to analyze the function of different organs. So in the heart, for example, we have these engineered heart tissues with human cells that we can use to understand, for instance, how the different cells in the heart communicate to yield heart function. We can use these models to create diseases and model these diseases in a human setting in the lab, which then allows us to understand what's going on and then even use those to screen for different drugs. And we can see what affects function or not. So in the case of the hearts on chip, we're looking at force of contraction. So these tissues beat, right? Just like a regular heart. So we can look at what affects force, what makes it better, what makes it worse. And by doing that, we can try to validate drugs. And one of the beauty of this is that, a lot of people do animal models before going into humans, and there's been a lot of recalls, specifically for the heart, because some of these drugs are toxic, and we cannot pick that up in animals because it's just a totally different physiology. So when we do these works with human cells, we increase our chances of picking up those side effects early on.
Okay.
So it really help us in a multi-pronged way to assess different drugs and to test how these drugs work.
Okay, excellent. Thank you. That's very exciting. So I understand that you are a cancer survivor. How has that personal experience shaped how you conduct research and influenced your work?
So, I had the traditional chemo and radiotherapy, and this is when I was in my 20s, right? And then after a certain amount of time, you get this clean bill of health, right? Like go and be happy, which I did. But then about, 15 to 20 years later, you have all these side effects of, there's certain specific chemotherapy drugs or even radiation. So radiation to the chest can affect the heart. And then I started having this cardiovascular symptoms. And I was looking back, and the literature is full of data. We know very well that, people that have received certain drugs at certain doses or radiation to the chest can have these cardiovascular problems. Okay. And some beautiful work has been done to look at these drugs directly in the heart cells or in the vessels, the cells that line our vessels. But, what really got to me was this delay. Some people have issues immediately. That is known, and that is dependent on their genetic background and etc. But this gap in this 15 to 20 years until you see some of these effects, and we got really interested on whether we could use these models, these in vitro models, to probe some of these questions. So what happens, maybe, these cells from the vessels and the heart, their communication is affected by these drugs. And that's really what we're seeing in the lab, that, the endothelial cells, which are lining our blood vessels, they're very active. Okay. And they react to both, chemo and radiotherapy in a certain way that even after the chemotherapy and the radiotherapy is done, they can still communicate to the cardiomyocytes and really decrease their function.
Wow, okay. So
it's really curious and really interesting to be able to study how, this is done. And we think this is related to, senescence, which people call it premature aging, which is not exactly that, but, it's kind of that perspective. Okay. And it makes sense if you think about the disease and how it kind of accelerates the appearance of cardiovascular issues. Right?
Okay. Yeah, that's really fascinating, the gap that you've identified between chemotherapy drugs, cancer drugs, and heart health. How do you envision further addressing this in the future?
Yeah, that's a great question. I don't know that I have a good answer for that, though, but I'll try. So in my lab right now, what we're doing is we're trying to look into these molecules and what these cells are releasing, that they talk to each other, and seeing how this is affected, and then trying to use these little chips to screen for potential molecules that could protect the heart or protect the vessel cells, so we can have a better arsenal of tools that we could use for this large population. There's a lot of people that have gone cancer treatment and they're gonna develop those issues, right? So can we do something now in vitro that will help that in the future?
Excellent, thank you for that. Looking ahead, how do you see your research and your technologies helping to both prevent and treat heart disease?
My lab works in many different areas, right? And I think that, we're using this multi-pronged approach, as I mentioned, to really look into, models in the lab that can help inform treatment in the clinic. But also we're advancing therapies using stem cells. So I think the next step, and we recently got funding for that, is to really try to, so we know these blood vessels from fat work, but if we want to make this a universal treatment, it would be great to be able to, recreate these blood vessels from stem cells, right? And there's been a challenge in the field, because even using the endothelial cells from stem cells, it hasn't been really successful. So we're now using a lot of state-of-the-art technology to understand how these vessels work really well in these different settings, in diabetes, in heart disease, and then gaining knowledge so we can try to coach the stem cells into really effectively forming vessels.
Okay, excellent. Thank you so much. It's been wonderful having you on the show.
Thank you so much.
To our viewers at home, you can watch more episodes on the Stem Cell Network's YouTube channel. Thanks for tuning in.